We're on the record now, I guess. So the reason I wanted to do that was in case anybody was going to tune in later and note that we still have an outstanding activity that must be completed for test 3. I believe that will close Wednesday at 11:30, this 2 days from today before Turkey Day. So please make sure that you complete test 3, part 3, which covers some things on the plastic stuff and a little bit of the biochemistry carbohydrate stuff that we had talked about. So make sure you fill that in. And then based on the things we talked about last Wednesday and what we're going to talk about today, I'm going to have some activity for us to do during the week of finals. I guess it'll be open all the final week, I guess. Why not? We're supposed to do it during some specific hour of class or whatever, but it'll just be open for you to do whenever you feel like doing it. So make sure I will send an announcement out when that is posted for our test 4, which is not comprehensive or covering everything we've talked about. It's just going to cover some of these things we've talked about with regard to energy and what we're going to talk about, parameters to measure energy, and maybe a little bit about gases if we get there, or if we don't, we won't. So we'll see where we are when that comes up. So now what I want to do is go to my slide thing and start showing some of my stuff on my PowerPoints. So I'm going to click on all these things like I always do. And I'm going to come down here and show my slideshow. And that's probably what you're seeing now, I hope. All right, so what we had begun to do last Wednesday was talk about energy. We talked about a little bit of the preliminaries with regard to energy, with regard to some classes that we can define energy and let them fall in of these classes. Globally, or overarchingly, if you like, there are 2 forms of energy, classes of energy, whatever you want to call them. There is energy of motion, which is kinetic energy. As the word kinetic implies, it's moving. That's what humans want. We get energy to move things around and actually to heat things up. And it turns out, as this definition is showing on this slide, heating things up is just moving them around. But that's what we want. We want things to be able to be moved by us. And in order for us to move objects around, it requires that we use energy to do so. So we get energy from sources to move objects around, bottom line. So the sources of energy are known as potential energy sources. And these include such things as springs, such things as gravity, such things as electricity, such things as light, such things as the energy stored in a nucleus, and most relevant probably to what we really are discussing here, the energy stored in a chemical bond, the connection between atoms to make molecules. So we harvest energy of motion from electricity, from gravity, from chemical bonds, or from springs, or from some stored source of energy. That's the whole point. Okay, so if we then just focus for a moment upon the idea of this types of kinetic energy, and kinetic energy again is motion. So we can think of an object moving in one of 2 ways. One way an object can move is what I call a concerted movement, meaning that the object is made up of matter. And if all the matter in the object concertedly moves in the same direction, I am doing work to the object. If I'm pushing a box across the floor, every atom in the box is moving horizontally as I push, and this is concerted motion of the matter. So whenever you have concerted motion, we're going to call that work or mechanical energy. Physicists kind of use those terms interchangeably. If, on the other hand, the energy of motion is deposited in the matter in a fashion so that it generates random motion in the object. And when I mean random, I mean random. I mean, if you could nanoscopically look at the matter, you would note that for every atom moving up and down, there's one moving left and right, there's one moving horizontally in the other direction, there's one moving diagonally in the other, in both diagonal directions. So all directions of motion are manifested into this matter. And when we do that to matter, we are depositing energy in the form of heat into the matter. So if you could look at matter when it is cold, and I put some nanoscopes on and look really closely at the matter, I would note that the atoms in the matter are dancing, and they're dancing completely randomly as this heat energy is distributed throughout the matter. For every atom moving left and right, there's one moving up and down, there's one moving sideways, one moving diagonally, blah, 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 blah. Now, as I heat the matter up, of course, if I touch it, my body has primal sensations that tell me, whoa, that's hot. And really the point is that nanoscopically, this hot matter is going to transfer momentum to my hand. If I leave my hand on there too long, I'll get too much momentum transferred to my hand. If I get too much momentum transferred to my hand, it'll invoke a chemical change in my hand, and that ain't good. So over the millennia, we have developed a primal instinct of sensation to tell us that's hot, get away. All right, so heat is, as we say here, it is randomized molecular motion, work, or mechanical energy is concerted molecular motion. Now, another thing I want to do is turn off my little thing that's hiding the words that are present at the bottom of the screen. So again, these are the two forms of energy that we desire. We call them kinetic energy, and humans use kinetic energy in the form of either heat or work. Okay, now I want to say a few words about this dude. You can see his name is Benjamin Thompson, and he was later given title by the British government. The Queen, or whatever you want to say, or the King, actually, was King George or whatever back in those days, George V. That would be Count Runford was the name he was given. And you can see the years which he lived. And let me just tell you a little bit of the story about this dude. First of all, our Benjamin Thompson was actually an American when things began. He was living in America. But when the Revolutionary War broke out in 1776 or whatever it was, he was sympathetic to the British cause and went back to England. So much like Benedict Arnold, probably the most famous traitor to the American Revolution that is known in general to the public, this guy also was a person loyal to the British cause. As a matter of fact, Ben Franklin's son was loyal to the British cause, but there were many other loyalists, as they called them. And you can take a history class to learn more about that. I'm not really the expert to turn to learn these things. But Benjamin Thompson returned to England when the Revolutionary War broke out. He was working for the British military at the time, and his job was actually to oversee the formation or making of cannons. So he was in the engineering brigade. He's a very smart guy, and they used his expertise to design and build cannons. And in the 1700s, when they made cannons, they couldn't cast steel yet. Maybe they did know how to make steel, but they couldn't cast it in the form of a cannon barrel. What they literally had to do was cast a solid chunk. I think they cast a solid chunk of iron, and then they bored the iron out. They got an auger, and they clamped the solid iron down, and then they turned this auger on the end of the solid iron and literally just drilled the cannon bore out of the solid piece of iron. Now, it actually turns out that it was kind of good the way they did that, because when they turned the auger, it would scrape the inside of the boring, so there was what they call rifling on the inside, where there were kind of spiral etchings. So when the cannonball would shoot, it would run along these etchings and it would give it a spin like this. And when the cannonball had spin like this, it came out, we call that rifling, and it made the trajectories of them so that when they flew through the air, the aerodynamics wouldn't make them knuckle in the air. They could cut through the air with the spiral motion much easier, much like when you throw a football. If you spiral the football, it cuts through the air very cleanly. So the same was true of cannonballs. Okay, that's a long story to really has nothing to do with what's going on here. What's going on here was that because of this hard work it was to bore the cannon out, they used horses. And the horses would walk in a circle. And when the horses walked in a circle, they had some gears and widgets and things, and it would turn the auger, and the auger hit the piece of iron, and it drilled it into a hollow thing to shoot cannonballs. Well, it also got extremely hot because there was a crazy amount of friction between the auger hitting the iron and the solid iron casting. And so what they would do is immerse the whole thing in water just to dissipate some of the heat energy. They would put the whole thing in water. And so the horses walked in a circle, the auger turned, the auger heated up the iron heated up the water. Well, what Thompson noticed, and this seems very simple now, but this was a revolution during the Revolutionary War. What he noticed was, hey, when the horses walk fast, the water gets hotter faster. And when the horses walk slow, the water gets hotter slower. So what he was noticing was that the horse's work, the mechanical motion of the horse around the track, could be translated into the heat of the water. So there was a transfer of energy in the form of work into the temperature of the water. And he went so far as to do careful experimenting, where the horses walked at various pace, and he would measure the temperature rise in the water depending on how much work, how fast around the horses went. And of course, he noticed when the horses walked around slow, the water got hotter at a slower rate. When the horses walked quickly, the water got hotter at a faster rate. And as simplistic as all this sounds, this was a profound advancement in the understanding of energy. So essentially what Rumford figured out was that work could be converted into heat. Now, he really couldn't prove that heat could be converted into work. That took another 50 years or so, when Robert Fulton and James Watt were perfecting the steam engine. What they realized from the steam engine was that heat from burning a fire could be converted into steam. And when you changed water into steam, it went from liquid to gas. And when it goes from liquid to gas, it goes from a relatively small volume to a relatively large volume. And when it goes from a small to large volume, it can push a mechanical piston. So heating the water made steam, making steam made it take up more space, making it take up more space could push on a piston, and then the piston could, by the wizardry of engineering, be designed to transfer that into movement work. So we were able to prove that heat could be converted to work, and later, we were first able to prove work could be converted into heat. That's what Count Rumford here proved. And then later, Watt and Fulton proved that heat could be converted back into work. And now what we come to the conclusion is, well, this is simply a simple matter of fact with regard to any form of energy. Not only can heat be converted to work and work be converted to heat, but what also is true is that literally all forms of energy can be interconverted. And so what developed from this time, from the 1700s, was the so-called science of thermodynamics. Now, it turns out that thermodynamics was a very important leap forward in our understanding of science. It was really the beginning of the maturation of science. Science really came to fruition with the development of this science that we call thermodynamics. Now, let's think of what the name thermodynamics implies. Thermo, of course, says something about temperature. And the idea is we're going to sense through temperature heat. So, as I mentioned last time on Wednesday, the easiest way in which we can measure energy is to do so with the thermometer. There are other ways we can do it. I mentioned like voltage and speed of an object. We can use those to measure the energy content of the object. But certainly far and away, our simplest way of measuring energy content is to have some knowledge of its temperature. So the thermo part of the word is implying something about temperature, and from the temperature, we're gaining information about the heat energy content. Then you'll notice that the second part of this name is dynamics. And so what that means with thermodynamics is heat transfer between objects. Now that's where the name originated from. More generally, we should think of the name thermodynamics as meaning energy transfer. And really, in general, the energy does not have to be in the form of heat. It's just so typical to us that the register of energy, the way in which we sense the presence of energy, is via the taking of the temperature of some system. Okay, so one of the basic premises of thermodynamics is that all forms of energy can be interconverted and changed from one type into another. So again, Count Rumford showed that mechanical work could be converted to heat. A little later, James Watt and Robert Fulton showed that heat could be converted into work via what we call the internal combustion engine. But the more general idea of thermodynamics is all forms of energy can be converted from one to another. And think about it. I plug in a lamp and I'm converting electrical energy into light. Now, not only that, if I put my hands around the light bulb, not only is the light bulb converting energy into light, I can tell by the feel of the light bulb, it's converting some of that energy into heat as well. I can use electric energy to convert into mechanical energy, of course. When you push the button in an elevator, the electricity is converted into moving you up and down between the floors. I plug an electric fan into the wall, the blades are spinning, and I start to push air around the room. I'm doing work on the air in the room using the electricity in the plug in the wall. And this can be generalized from one form of energy into any other that I want. So you might even want to try to stump me by just, okay, you named all these forms of energy and you're claiming how all these forms of energy can be converted from one form into another. Well, then show me how you can convert, let's say, gravity energy into nuclear energy. Gravity is a form of potential energy. Nuclear, the energy in the nucleus is a form of potential energy. How in the world can you convert gravity into nuclear energy? Well, guess what? That's what the sun does. In the sun, there's a massive amount of hydrogen atoms being pulled in on each other by the immense number of them. There's so much incredible gravitational force in the center of the sun. The hydrogen atoms are squeezed so closely together that they fuse into helium. That's how the sun works. It changes hydrogen into helium and puts two hydrogen atoms together to make a helium nucleus. So there's an incredible amount of energy, of course, released in the sun. And this is the result of gravity being changed into nuclear potential energy. Now you should even take it even a step further. Now energy and light radiate from the sun 93 million miles to the earth and get hit by a plant leaf, and the light energy gets converted into chemical bond energy to build the glucose molecules that are used to make the plant's stems and leaves and things of that sort. Then an animal comes along and chews the plant leaves and converts the chemical bond energy into mechanical energy. And on it goes. All these forms of energy are constantly interconverted between each other. Okay, we say that work and actually mass and energy can actually be interconverted as well using one of the most famous equations of all time. We're really not going to delve into this. This is really not a thermodynamic equation. It's a relativistic equation, but mass can be converted into energy using, of course, the most celebrated equation of all time. We're going to focus on energy forms being interconverted between each other. So here is what the premise of this ultimately says. All the energy in the universe is here. We're not creating any new energy in the universe. And first of all, you should note that the universe is all encompassing. When I say the universe, I mean everything, not only, of course, what we recognize here, and this might be thought of as our universe, this world in which we live, but I'm talking about all surrounding space. So we have this concept of this vast universe surrounding us, which seems to be infinite, but seems pretty impossible to believe would actually be infinite. I would really have a hard time believing if you went far enough out and you kept going and kept going and kept going, that you wouldn't come back to where you started from. It just makes much more logical sense to me that the universe has to eventually be circular. It doesn't make any sense at all to me that it could be any other way. But in any event, that's another philosophical question for much deeper time of thought, maybe a few beers to really grasp. So my point is that in this vast encompassing universe in which we claim to live, there is energy. But we are not at any time creating any more energy. All the energy of the universe is already here. All we are doing is interchanging it. I am converting gravity into nuclear. I'm converting the nuclear energy into light energy, nuclear energy into heat energy. And then I'm converting the heat energy and light energy into chemical energy. Then I can burn the chemicals and make electrical energy, and on it goes. So all we are actually doing is transferring energy from one form to another. So all the energy of the universe is here. There's only a fixed amount of energy in here. We are not creating energy. We are actually not destroying energy either. All we are doing is moving energy from one form into another. This is the first law of thermodynamics. We have a universe which operates under what we will call conservation of energy, meaning all the energy is here. We're just moving it from form to form. We're never making any new energy. We're just changing it around from one type of energy into another type of energy. Okay, so if we were to measure the energy unit, we would use what we call the joule. And it turns out that the joule is, as we talked about many moons ago now, the joule is a derived unit. It's a combination of base SI units. The base SI units, which energy is a combination of, are mass, length squared, time squared, divided by time squared. So joules of energy can be measured, and that's the basic SI unit, using mass, length, and time in the prescribed SI units. If I measure mass in kilograms, measure distance in meters, which is a little more than a yard, kilograms about a little more than 2 pounds, and I'll measure time in a second, and we all know what a second is. So if I have 1 kilogram meter squared per second squared, that would be 1 joule of energy. Now, a joule of energy, again, as we will see here, is not very much energy, but if I'm going to talk in SI units, that's how I should measure it. Now, one way that you can recognize the units in a joule, if you happen to know a little bit about energy formulas, the kinetic energy an object possesses that is moving with a velocity v and has a mass m, the kinetic energy is 1/2 mv squared. So the units that you see there reflect mv squared, mass in kilograms times velocity in meter per second squared, would give you the combination of units that you need for a joule. Okay, now what I show in this table are the energetic units, and this is how bad it is. I better look closely at this. And one thing you should learn about what this table shows, now, of course, if I asked you anything about these, you could look it up on this slide. I don't even know if I would do such a thing, but this is a table showing various amounts of energy and their equivalent in joules. So it says that the energy of sleeping for 1 hour is 10 to the 5th joules. Okay, that is 100,000 joules. So every hour that you sleep requires that your body use 100,000 joules of energy to beat your heart, pump your blood, regulate your temperature, push your lungs in and out, and so you can breathe. So as we all know, no one has ever claimed that sleeping for an hour was a great way to get exercise. But according to this scale, it takes 100,000 joules of energy for you to just lay completely still at rest. Well, not completely still, we know what I mean, but to lay at rest for 1 hour. Now, it turns out what this is saying is that the joule is a very tiny unit. Okay, it is a very tiny unit. And so typically scientists don't like to use such tiny units because the numbers end up being really big when you use tiny units. So scientists have taken to other units to describe something like this process so that we can use these other units to make it translate into smaller numbers when we're trying to describe how much energy you might be using, for instance, when you're sleeping. And the most familiar unit to us as consumers that we would use in place of joules for energy are calories. Calories are the familiar way in which we can measure this type of unit. And if you wanted me to translate that, I can do it in some rough, quick head math. 100,000 joules of energy, which is the energy to sleep for an hour, would translate into 20 calories of energy. So every hour that you sleep, you burn about 20 calories in your body while you're sleeping for that hour. Okay, so then if we see up the scale a little bit, the energy in a serving of pasta or a donut is 10 to the 6th joules. So what that is kind of saying, if you could translate that into calories, we got about 200 calories in those things. That might be a little low, depending on how much sugar you put on it, and or other things you might put on there, meat in the sauce or whatever. But that would be roughly the kind of transitions we would make between joules and calories on this particular scale. So you notice in a gallon of gas, there are 10 to the 8th calories. So what's that mean? That sounds like, I'm sorry, 10 to the 8th joules, excuse me. The scale we're using are joules. So it says the energy of a gallon of gas is 10 to the 8th joules. So again, that would be like 20,000 calories of energy, roughly speaking, if I translated that with some quick math from the idea of joules into calories. Now, just interestingly, keep going up that scale there. The energy use per person per year in America, notice, is 10 to the 11. That's almost a 10 to the 12 is a trillion. So we're each using about almost a trillion joules of energy. Notice how much energy reaches the Earth from the sun. First it says per second, but the second one, so that it's 10 to the 17 joules of energy reach the Earth from the sun every second. That is a massive amount of energy, as you can see. And if you translated that into how many seconds are in a year, that would probably be about 10 to the 21 joules of energy reaching the Earth every year from the sun. That's a crazy amount of energy. Notice the energy consumption, though, in the US per year. That's a crazy amount of energy, especially considering when you look at the world reserve of energy. Look at the line that says the energy consumption by the US, and then look at the line above it, which says the energy reserve of the world. And that's kind of taking into account how all the solar energy from the sun has been converted into chemical bond energy and then ended up in dinosaur goo and plant goo that we dig out of the earth as fossil fuels. I've already gone into a major rant about fossil fuel consumption in this country, how it's out of control, how it's really selfish of the United States to think that they can use so much of the world's energy without consequence. So I'm not going to get into that anymore, but really there's a limited amount of fossil fuels left. We should be acting as good stewards, especially to our future generations. We should be taking steps now to remediate and curtail our use of these things, but I can't stop it. I mean, I can only just rant about it. So hopefully soon people will wise up and take some steps to take care of how much oil we have left and how we are using it, particularly with regard to the fact that, as I said, China now wants it, India now wants it. We're in trouble because they outnumber us substantially. Okay, so anyways, let's take a look at how we can measure heat in an object compared to the temperature that the object possesses. Okay, I think it's pretty plain to see. When you heat something up, it changes temperature. The more heat energy you add into the object, the greater the change in temperature the object undergoes. But there are some weirdnesses to what occurs. Like, for instance, on Wednesday of last week, we talked about phase change of state from, say, solid to liquid, liquid to gas, solid to gas. I can melt something as it goes from a solid to a liquid. I can boil something as it goes from a liquid to a gas. Now, when these phase changes are occurring, all the energy you put in goes to breaking the relationships between the atoms to put them from the more ordered state into the less ordered state. So I break the attractions between the solid molecules, and they can now move relative to each other in the liquid condition. I break the attractions between the liquid molecules, and now they can move relative to one another in the gas condition. Okay, so the interesting thing is when I am doing so, if you monitor what's going on with the temperature, something very interesting occurs. If I take a liquid, and I think we're all familiar with this, and I turn on the stove, the liquid starts getting hotter and hotter and hotter. And if I put a thermometer in the liquid water on the stove, I will note that the mercury goes up more, or the alcohol, whatever kind of thermometer it is. In any event, the temperature goes up and up and up as I put more heat energy into the liquid. But something mysterious and magical happens when the liquid begins to boil. At the temperature of the phase change, the temperature no longer rises. So I start the water out of the tap at 25 degrees C, 75 degrees Fahrenheit. I begin to put heat into the water, and the temperature of the water goes up and up and up. And as it approaches 100 degrees C, or 212 degrees Fahrenheit, the temperature now magically ceases going up. It doesn't go up any further. And I can crank the heat up as much as I want. It doesn't matter. The temperature will sit at 100 degrees C or sit at 212 degrees Fahrenheit. Why? Because all the energy you're putting in the form of heat no longer goes into raising the temperature of the liquid. It goes into breaking the attractions between the water molecules and allowing them to change from the liquid to the gas. So as long as the water is boiling, the temperature remains fixed at 212 degrees Fahrenheit. The temperature remains fixed at 100 degrees C. It won't go up from that point until all the water has evaporated. Now the steam can get hotter than 100 degrees C as I continue to dump heat energy in. So when the phase change is occurring, the temperature halts, as we say, or remains at a fixed value. So that's one weird thing which occurs while you are dumping heat energy into an object. But there are other weird things which happen. And one of those goes back to a slide I showed on Wednesday. And what that was is the fact that, let's suppose, again, you go to the park, and there are 3 benches sitting there in the park, all in the sun. And one of the benches is wooden, one of the benches is plastic, and one of the benches is metal. And then you run your hand and touch each of the benches. You touch the wooden bench, you say, "Oh, that's warm from the sun." Then you touch the plastic bench and say, "Oh, that's hot. It's hotter than the wooden bench." Then you go over and touch the metal bench and you go, "Wow, wow, that sucker is so hot I might get a burn from touching that metal bench." Now, the interesting thing is they're all being exposed to the same heat energy. The sun is the same distance away from all 3 of those benches. They're all getting bombarded with the same amount of radiation from the sun, yet the temperature on the wooden bench is lower than the temperature on the plastic bench, which is lower than the temperature that was on the metal bench. You could also try this experiment, but I wouldn't recommend doing it unless you're very careful. That would be put some water on to boil on the stove and put a spoon in the water. Then as the water starts to warm up, you put your finger in and feel the temperature of the water, then feel the temperature on the spoon. Spoon will be way hotter than the water. Now, what you need to note is when I say hotter, what I mean by that is, how do I measure hotter? I measure hotter using the scale of temperature. So temperature is how I sense, of course, whether something is hot or cold. And when I say the spoon is hotter than the water, it is because that the spoon is at a higher temperature than the water. Now, does that mean that the spoon is being exposed to more heat from the surroundings than the water. No, it doesn't. They're being exposed to the same amount of heat from the coils of the stove or from the flame on the gas stove as each other is experiencing. However, there's some property to the metal of the spoon which makes it be at a higher temperature than the water is when they are exposed to the same amount of heat. Okay, so what scientists use to measure the phenomenon of how hot an object gets as you dump heat energy into it, we call that the heat capacity of the object. So the heat capacity is the ability of a substance to store heat, and what we will say, without it being sensed. So what it means then is it stores heat without raising its temperature. The higher your heat capacity, the lower your temperature change upon the input of the same amount of heat. So materials with high heat capacity don't get as hot as materials with low heat capacities. Okay, so the symbol of heat capacity is a capital C, and there are some things that affect the heat capacity of a material. The first being how much stuff you have. Okay, so think about it this way. If I am going to boil crawfish, I put this pot of water on the burner. And simultaneously, I'm going to make some tea. I'd rather drink beer, but if I drink some tea to have with my crawfish, I put a little pot of water on the stove. I turn on the burner to the pot on the stove and on the crawfish pot. Guess which one takes longer to get hot? Of course, the more water you have, the slower the temperature change in the water. Your mom and them know that. The more water I'm trying to boil, the longer it's going to take me to raise the temperature to boiling. So very obviously, when I have a certain amount of stuff present, the more stuff I have, the higher its heat capacity. It will take it longer to reach a higher temperature. As a matter of fact, this is direct proportional. Double the amount of stuff, you will cut the temperature change it undergoes by 1/2. Triple the amount of stuff as you started with, it will cut the temperature change with the same amount of heat input by 1/3. So there's a nice proportionality between that and the amount of material. Secondly, the heat capacity of a material is some natural function of what the material is. Now, to recognize this, we'll go back to what I said earlier about a plastic bench, a wooden bench, and a metal bench. The wooden bench didn't get as hot as the plastic bench, and the plastic bench didn't get as hot as the metal bench. There's something different to the makeup of the material of the wood compared to the plastic compared to the metal, which makes them hide a change in temperature more effectively. Now, if you want me to explain a little bit about why certain things feel hotter than others upon the same input of energy, remember, heat is motion. So if an object is flying around in a chamber and it strikes an object in that chamber, it imparts heat on that object. So for instance, this week upcoming, on Thursday, you stick a turkey in the oven and you turn the oven on and it cooks the turkey. What's really happening there is that the coils in the oven give energy to the air in the oven. When the oven is off, and you could now look nanoscopically at the air, you'd see the molecules of air are zooming around in the chamber, zooming, probably moving at the speed of sound, roughly, in the chamber. And now when you turn the oven on, they're really zooming. They're moving like crazy in there. The hotter the oven is, the faster the air in the oven is moving. And now when you put the turkey in there, guess what happens? This air slams into the turkey. It imparts so much momentum into the turkey that it invokes a chemical change in the turkey. So the turkey is changed the meat of the turkey changes from the impact of the air molecules at this high temperature, and it changes chemically the makeup of the turkey meat, cooking the turkey. So that's what happens. The hotter you make the oven, the faster they're moving around. The faster they're moving around, then the more energy they contain. Now, let's suppose there's other molecules in there like water molecules, and let's pretend my arms are the H's and my big body is the O. Now, if I put energy into the water molecule, it can slam into the turkey, but also it can move the H next to the O and move the O next to the H. It can wiggle the O's like this to the H to the O's, wiggle the H and O's like this, wiggle the H and O's like this, and that's not flying the H and O around the chamber. So if I put the energy and hide it in internal motion of the H's and O's relative to external motion of the whole thing slamming into the turkey, then the temperature of the water molecules doesn't seem to have gone up as much as it would have if it just sent them flying around in the oven chamber. So that's the difference of how heat capacity in some materials can be hidden. It can be hidden in internal motion rather than external motion. All right, so that's the story of where heat capacity is going. So there's a magic formula that relates the heat energy, which I'm giving a symbol Q, and that's kind of unfortunate because we gave that symbol Q for electrical charge as well, but this is what physicists do. And it's kind of interesting because good conductors of electricity are also good conductors of heat. So that might have something to do with it. If you're a good electrical insulator, you're a good heat insulator as well. And maybe we'll have more to say about that later. So this Q that you're seeing here is not electrical charge. It's conducted heat. And the heat, as you can see, is equal to the heat capacity, which I said was capital C, times a quantity delta, which is the Greek triangle for delta T. And what delta T means is the final temperature minus the initial. Okay, so the heat you put in is equal to some heat capacity constant times the change in temperature that the matter undergoes. Notice if you double the number Q and you leave C the same, you would double the number delta T. Putting in twice as much heat changes the temperature twice as much. Cut the number Q by 1/4, leave the C the same, you would have to cut the number delta T by 1/4. Put in 1/4 as much heat, the change in temperature that the matter will undergo is 1/4 as much. Okay, so Q can be a negative or a positive number, and that's saying whether energy is put in or energy is being removed. So let's think of the logic of what that means. If energy is being removed, that's what we call an exothermic process. Exothermic means heat released. If an object releases some of its heat energy, its temperature will go down. If its temperature goes down, TF, the final temperature, is lower than TI, the initial temperature. So if TF is less than TI, delta T is negative. So if delta T is negative, that goes hand in hand with Q being negative. So when a process is exothermic or releases heat energy, its final temperature is lower than its initial temperature, its delta T is negative, and its Q is negative. Now on the contrast, if you have an endothermic situation, you add energy to the system. If you add energy to the system, then the final temperature will be greater than the initial. It gets hotter. If final is greater than initial, and then you calculate delta T, you're going to subtract a little number from a bigger number, delta T will be positive. And that's saying if delta T is positive, Q is positive. So for endothermic processes, TF is bigger than TI, delta T is positive, Q is positive. Okay, so sometimes we write it with M times SH for C, and the M tells us how much stuff we have. The SH tells us how the stuff is built. We call that its specific heat. So sometimes we use the formula Q equals M times SH times delta T. We're not going to use the formula anyways, so it doesn't really matter. But sometimes scientists use it in a form that you see at the bottom of the page. Now, what I do want to show are some numbers for the values of this so-called specific heat. This says something about how well materials hold heat, energy. The bigger this number for C or specific heat, the less temperature change a substance will undergo when you add a given amount of heat to it. Now you'll notice the size of these numbers are all relatively small. These numbers are not big, but you should notice that, for instance, the number, let me make sure I'm not going to read them incorrectly, the number for liquid water. The number for liquid water is 4.18 compared to the number that I'm showing here for, let's say, copper, 0.38. Now, so what you compare those numbers for liquid water to copper, it says that the water has a specific heat or heat capacity 4 times, or sorry, not 4, sorry, scratch that, over 10 times as big. If you take 0.385 times 10, it'd be 3.85. Still not as big as the number for water. So here's what that means. If you put the same amount of heat into copper that you put into water, you will experience a change in temperature in both of them. Put the heat in, they both get hotter. But since the heat capacity of copper is 1/10 the heat capacity of water, the copper will get 10 times hotter than the water if you use the same mass copper and water. So let me again state that and think about it for a moment. Let's suppose I have the same mass chunk of copper as I have mass of water. Let's suppose I put an amount of heat into the water to make the water go up 10 degrees C. Simultaneously, if I put that same amount of heat into the copper will go up over 100 degrees C. That's because water has an amazing ability to hide heat energy without changing temperature. Amazing. This is one of the most important aspects of this planet. Why? Because this planet is covered with water. 75% of the surface of the water of the planet is covered by water. And not only is the planet covered with water, it's incredibly deep. The water in the oceans in some points goes down 5, 6, 7 miles. It's an incredible amount of water on this planet. And as we're showing here, water has a very high heat capacity. And what that means is the planet can absorb a huge amount of heat from the sun without undergoing a dramatic temperature change. Now, think of the ramifications of that. The moon is the same distance from the sun as is the Earth. Now, sometimes it's a little closer, sometimes it's a little further. On average, the moon and Earth are the same distance from the sun. The moon has no water. Earth covered with water. The temperature on the Earth in degrees C from night to day changes. Now, again, this is in degrees C, 25 degrees C. That's a pretty dramatic change from day to night. That'd be like 40, 50 degrees Fahrenheit. That's a pretty dramatic change from day to night. Here, it can happen, I know, but still pretty dramatic. Well, meantime, on the moon, where there is no water, the change of temperature from when the sun is shining on the moon to when the sun is not shining on the moon, we're talking hundreds of degrees C, 400 degrees C difference. That's degrees C. So that's a crazy dramatic change in temperature from night to day on the moon compared to the change in temperature from night to day on the Earth. Now, if you don't appreciate the fact that developing life on a planet, suffering those kinds of drastic changes in temperature, if you don't think that that would impede the chance of life flourishing and evolving, I think you're sadly mistaken. So if the conditions on this planet, including, of course, the atmosphere of oxygen, but also the copious amounts of water present on this planet, these are the ingredients, at least for the forms of life that we understand, these are the ingredients that are absolutely tantamount for the flourish and development of advanced life systems. No question about it. Okay, so an alternative to the energy unit, as we talked about in joules, is the so-called calorie. And the way a calorie is measured is it's the heat required to raise a gram of water 1 degree C. So if I input an amount of energy that takes 1 gram of water, which, okay, how much is a gram of water? It's a milliliter of water. It's really nice that water has a density of about a gram per milliliter. So if you have a 500 milliliter bottle of water, it's got 500 grams of water in it. And for every 1 gram of that water, if you want to raise its temperature 1 degree C, put in an amount of energy, which we will define to be a calorie. The same thing is true in reverse. If you want to cool 1 gram of water down by 1 degree, you have to remove from it 1 calorie of heat. Now this number, turns out, scales really nicely. As we say here, if I want to take 10 grams of water and raise it a degree, I should put in 10 calories. Okay, so it scales any way you want to think of it. If I want to take 1 gram of water and raise it 10 degrees C, put in 10 calories. Okay, so you can scale this number any way you want. Okay, so what this says is the comparison between joules and calories is such that if you have 1,000 1 calorie of energy, sorry, not 1,000, that's 4.184 of these joules. Now, it turns out that this is still too small of an energy unit, particularly if we're going to hamburgers or a donut or any kind of food content, which we want to gauge how much motion energy we can get out of it. So in the food industry, we multiply that by 1,000. 1 food calorie is actually a kcal, or 1,000 of these units I'm talking about. So in food calories, you have to take 1,000 grams of water and raise it 1 degree C. And if you raise 1,000 grams of water by 1 degree C, then you're putting in food calories. So if you take 1,000 grams of water and raise it, the water temperature from say 25 to 35 degrees C, you raised it by 10 degrees, you had to put in 10 food calories to raise the temperature of 1,000 grams of water 10 degrees. So this is literally how the FDA figures out the caloric content of food. Literally. They take a sample of food, put it down into a chamber that what they call a bomb calorimeter. Then they pump oxygen in with the food. So I got a pile of cheesy poofs that I put in the chamber. And then I pump oxygen in with the food, put an ignition wire down into it, put a nice stir to mix up the temperature and spread it around evenly. Have my bomb down in the water. And then I put my food in there and I fill it with water and I get a thermometer and I light the fuse on the bomb. It burns the food inside with the oxygen. The heat from the burning food warms up the water. And if I put exactly 1,000 grams of water or a kilogram of water in the calorimeter, I measure how high up the temperature goes, and it tells me how many calories of food are in the food sample. So if the kilogram of water went up, the kilogram of water goes up by 50 degrees, when I burn that food in there, I put a 50-calorie sample of the food in the chamber. If I put food in there, put the oxygen in, put the fuse in, light it up, it goes up by 75 degrees C. I put a 75-calorie chunk of food in the chamber. So this is how, literally, how the FDA determines the calorie content of any food sample that we are using. So the specific heat of water, as we say there, is 1 calorie per gram per degree C. Every 1 gram of water goes up 1 calorie. So if I have a kilogram of water, I'm going to be going up 1 food calorie per kilogram per degree C. Okay, so when you look on the side of your box of food, it will tell you information about the calorie content present in those foods. And what the government has determined from burning enough different types of food is the average calories it takes for the carbohydrates in the food. Remember, those are your sugars and your starches and things of that type. That's your carbohydrate content. The fat content of the food, how many kilojoules there are per gram of it, or how many kcals per gram there are. Now remember, a kcal per gram is a food calorie per gram. So we should look at the final column on the right and not think of that in terms of kcal, but of food cal. So for every gram of carbohydrate in your food, it has 4 food calories. For every gram of fat in your food, there are 9 food calories. For every gram of protein in the food you're eating, there are 4 food calories. So, for instance, I have a glass of milk, or the cup of milk, 8 ounces, I guess. It has 12 grams of carbs, 9 grams of fat, and 9 grams of protein. Remember, again, the food calories are the kcals. So I can take my 12 grams of carbohydrates, multiply by 4 kcals per gram. That's what that number says. So that's 48 food calories from the carbs in the milk. I could take my 9 grams of fat times the 9 food calories per gram, and I would get 81 food calories from the fat in the milk. This must not be skim milk, obviously. Then I can take my 9 grams of protein from the milk, which is part of the amino acids and all the good stuff that is in the milk from the cows. 4 food calories per gram. There's 36 food calories from only the protein. Add these all together, and it would tell me that my cup of milk has 165 food calories. So again, this is exactly what the USDA does to determine the caloric content of your food sample. Okay, now let's say a few things about the conditions on which we measure phases of matter. Let's say a word or two about temperature. Let's say a word or two about pressure. Okay, so what is temperature? It's, as we've been talking about, how hot or how cold an object is. So the more energy content the material possesses, the higher its temperature. Temperature, as I say here, is a relative measurement. Now, what does I mean by that? I typically design a temperature scale, and I measure temperature on that scale. There are a couple scales that are commonly used: the Fahrenheit scale, the Celsius scale, and the Kelvin scale are the typical ones that we commonly use in science. So maybe we'll say a word or two about these things. And of course, what we're going to do to measure our temperature is in some way use a device we call a thermometer. Now, how does a digital thermometer work? A digital thermometer uses electric current. And it turns out, might be a little bit weird, but it turns out that when electricity flows in a circuit, that is a temperature-dependent phenomenon. And it might seem a little bit weird, but the hotter you make a circuit, the less flow of electricity it is allowed to experience. And what we can think of is when you have a cold circuit, the atoms are sitting nice and still. And now the electrons can hop from atom to atom to atom, and you can have a current, a flow of electricity, very conducive to flow when the atoms are sitting still. When I heat the conductor up, the atoms are moving around. And as the atoms are moving around, the movement of electrons through the conductor is deterred. So the jostling of the individual atoms as I heat the circuit makes it harder for a current to flow through them. So as the temperature of the circuit goes up, the conductive ability of the circuit goes down, the current goes down. So when you place an electric thermometer, a digital thermometer, into something to measure its temperature, it heats the circuit up, which is allowing current to flow, and then it measures how much current is allowed to flow and decides what temperature it must be when that amount of current is flowing. So that's how a digital thermometer works, due to the resistance of the conducting material. As the heat increases, the resistance increases. As the resistance increases, the current decreases. And as the current decreases, it knows how to convert that into the temperature that the sample is measuring. Now, if you don't use a digital thermometer in the old days, you use a liquid thermometer. How does a liquid thermometer work? Well, it works with an expanding liquid. As we're all, I hope, aware, when you heat objects up, they expand. They expand more and more and more depending on certain characteristics of the material. Gases expand a lot. Solids and liquids expand a little bit, but if you design the liquids correctly and put them in a nice thin tube, they will expand quite dramatically. So as you heat the liquid in the thermometer, the atoms and molecules in the liquid bounce and jump and bounce and spread out apart from one another. So you can begin to mark off the spread and count that as the temperature of the sample. So a liquid thermometer uses the expansion of a liquid, which increases as the temperature increases, to tell a scale that we can measure for the temperature. And who came up with the original scale? Well, should be a familiar name to us. The individual who first invented the thermometer and then put it onto a scale that can be measured, was Daniel Fahrenheit. And so he put mercury in a tube, and when he put the mercury in the tube near a hot object, the mercury expanded greatly. When he put the mercury in the tube near a cold object, it contracted to a much smaller volume, and he just decided to mark them off to some known temperatures. So what he did was he took the coldest thing he could make, which was saturated salt water solution, not pure salt, pure water, but he took salt water, put ice into the salt water, put the mercury thermometer in there, it contracted down, and he marked that off as 0. Then he put it in his armpit or some body cavity, let it expand as it warmed, and he actually called that 96. Now, we've changed that to more like 98 these days, but originally, when he made his thermometer, he called that 96. And so on his scale, pure water would be in equilibrium with ice at 32 degrees C. Salt water was in equilibrium with ice. I said degrees C, I meant pure water was in equilibrium with ice at 32 degrees Fahrenheit, excuse me. And on his scale, salt water was in equilibrium with ice at 0 degrees F. You got the most contraction in salt water. It expanded out a little bit in pure water. And then when he boiled the water, it would expand to the point where that would be a measurement of 212 degrees Fahrenheit. Okay, so here's what it looks like, folks. It looks like that's going to be quitting time. Got a minute or so, but that's enough. Remember to please go out, complete test 3, part 3. Remember, next week I'm going to have some activity for us to do for our final exam, and I will send out a Moodle announcement when that is available to you. And I at least enjoyed myself this semester. I'm sure this is not particularly your cup of tea, but I hope you made it through this, and I hope you learned a little bit of something out of this. And I hope you're very successful in all the things that you want to do with your lives in the future. So again, tune in to Moodle. I'll let you know what the final is, and then it'll be posted and you can complete it after the Thanksgiving break. So until then, peace out.